Chapter 5, Odd Number Problems 15 through 23. 15. For a sample with a standard deviation equal to 8, a score of x equals 65 corresponds to a z-score of 1.5. What does the sample mean? So again, similar to a previous problem, we should begin with a visual interpretation of what we are provided. So here, the mean in the center is the value that we want to solve for. The distribution has standard deviation equal to 8. Excuse me, let me put the correct notation. It's a sample, so we're going to put S is equal to 8. And then we've indicated that a score of 65, so a score of 65 is the same as, if we consider the z distribution, is 1.5 standard deviation units above the mean. So, given that, we can approach this a couple different ways. Z-score of 0 for the mean. We can consider, again, similar to a previous problem of what is the distance between these two scores, right, in terms of points. We can address that by taking into consideration how many z-scores difference it is from here to here. And I made that a little bit longer than I should have so that it's equivalent. So again, we're talking about the distance between here and here. Oops. Now I've just made a big mess. Let's start over just to make things a little more comparable. We have our mean here. So we have a distance from here to here, right, in terms of z-scores and then in terms of raw score points. So this would be 0, this would be 1.5. Okay. So we could try to figure out what this distance is equal to in terms of points by considering the score of x, right, again this is just distance, the score of x equals 65 is 1.5 standard deviation units above the mean. So we could take 1.5 multiplied by 8 and recognize that that's equal to 12 points. So what we're saying is that from here to here is 1.5 of these, 1.5 of those, which is 12 points. So in terms of raw score points, from the mean to a score of 65 is 12 points. So we could just say 65 minus 12 to figure out what the mean is equal to, which in this case would be 53. Another way that we could consider this is to use an equation. We could use our equation x is equal to the mean plus our standard deviation multiplied by our z-score. We can replace variables and say that a score of 65 is equal to the mean, which we'll pretend like we don't know yet, multiplied by 8, which is standard deviation, times its location of 1.5 standard deviation units. So again, we can simplify this and say 65 is equal to m plus 12. And if we're interested in solving for m, the sample mean, we would simply subtract 12 here and 12 there, and we would get 53 is equal to our sample mean. Okay, so again, we can approach it visually to figure out the z-score distance and equate that to raw score points difference, or we can utilize this equation to replace variables and solve for the missing variable. Number 17, for a population with a mean of 70, a score of 64 corresponds to a z-score of negative 1.5. What is the population standard deviation? Again, just as we've done in the past, let's visually represent what we have or what we're working with. So we have a mean of 70 here in the center. We have a score of 64, which would be to the left of the mean, 64. Which is understood to be negative 1.5 standard deviation units below the mean. And again, what we're interested in finding out is what is each standard deviation equal to. So again, if we think about distance, we see that from here to here, that's 1.5 of these unknowns, which is the same as the distance from here to here. So the difference between 70 and 64. So if we just think of point difference, 70 minus 64, we understood that that's 6 points, right? It's the same as 1.5 standard deviation units. So if we just want to find out what 1 standard deviation unit is equal to, we would convert our 6 points divided by 1.5, and that gives us 4 points. 4 points. So again, we're saying one of these and a half. So 1 would be 4, plus half of 4 would be 2, is equal to 6, right? So just working backwards to understand what we just did here. That's one way to approach this. Another is to, again, use the equations that we were taught in this chapter. So z equals x minus the mu divided by standard deviation. Again, if I want to solve for standard deviation, just move these variables around so that I then have what I need. So what it ends up looking like, the standard deviation is equal to x minus mu divided by z. So again, standard deviation is the same as our score, which is 64 minus 70, excuse me, divide by negative 1.5. So again, 64 minus 70 is equal to negative 6. Divide by negative 1.50, and we get positive 4. So again, whether we approach it as a visual interpretation of distance, or we actually use our equation to replace variables to solve for what standard deviation is equal to, right? Both processes lead us to the exact same answer, and hopefully you see how we came up with 4. Again, 4 and half of 4 is 6, and that's the distance that we see here, 6 points distance below the mean. Number 19, in a sample distribution, x equals 56 corresponds to z equal to 1, and x equals 47 corresponds to z equals negative 0.5. Find the mean and standard deviation for the sample. So we're going to, again, visually interpret what we have been given. So we have a distribution where the mean is unknown. We say that if we go 1 standard deviation unit, we get a score of 56, and half a standard deviation below gives us a score of 47. So again, this is equivalent. Its new label is 0.5 below the mean, 0.5 standard deviation units below the mean, and here 1.0 standard deviation units above the mean. Again, this is a same process of finding the distance in points and dividing by the distance in standard deviation units to equal 1 standard deviation unit. So we don't have the mean to work with, but we could consider the distance from this score to this score. So the difference between 47 and 56. And then understand what it means in terms of standard deviation units. So first, if we just think about the difference between 56 and 47, if we do that simple calculation, that's a 9-point difference. So this is 9 points between a score of 47 and 56. And in terms of its equivalent of standard deviation units, we wouldn't take 1 minus half, right? We want the whole distance. So from here is 1 standard deviation unit, and then to here is half a standard deviation unit. So this is a total distance of 1.5 standard deviation units. Again, from here to here, and then from there to there, total is 1.5 standard deviation units. So similar to what we did in the past, we took the distance between the two scores, that's equal to 9 points, divide by 0.5 to get what 1 standard deviation unit is equal to. So that would be 6 points. Okay, so we've concluded that standard deviation is equal to 6 points by taking the difference between the two scores in point difference and divided by the distance in z-scores, in standard deviation units. Next, what we need to figure out is what does m equal to? What is m equal to? So we can use these two scores of 47 and 56 to figure that out. So first, if we say x is equal to m plus standard deviation multiplied by z, if we replace variables, if we work with 56 first, 56 is equal to the mean plus our standard deviation of 6 points times our z-score, which is 1. All right, we would say 56 is equal to the mean plus 6. So if we want to find out what the mean is, we would subtract 6 here and subtract 6 here and come up with 50, right, is equal to m. So we are considering that the mean, sample mean, is equal to 50. Let's use the other x value to confirm that this is true. M plus s multiplied by z. Now let's take into consideration the score of 47. 47 is equal to the mean plus our standard deviation of 6 points multiplied by our z-score of negative 0.5. Okay, so 47 is equal to m, and then minus, right, 3. So 0.5 negative multiplied by 6 is negative 3. So if I want to find out what m is equal to, I'm going to add 3 here and add 3 here. And again, we say 50 is equal to our sample mean. So we've concluded now that in this distribution, given the distance between two scores, one above and one below the mean, we could take that and divide it by their equivalent distance in standard deviation units to figure out what one standard deviation unit is equal to. Using that value or that variable, we were able to use the other equation of solving for x, replacing variables, to then solve for our sample mean. Number 21, a distribution of exam scores has a mean of 78. If your score is x equal to 70, which standard deviation would give you a better grade? All right, so visually, if we have a distribution with a smaller variability, standard deviation equal to 4, and we have a distribution mean of 78. Our score is 70, so if we go out one standard deviation unit below the mean, that puts us at 74. That still doesn't capture our score, so we go another standard deviation unit below. So again, this would be -1 standard deviation unit, and -2 standard deviation units puts us at a score of 70. Let me clear that up a little bit. So 2 standard deviation units below the mean is equal to a score of 70. We can do it this way, or now that we know our equation, we can say z is equal to our score, 70, minus 78, divide by 4. So z is equal to 8 divided by 4, and that would be -2. So in this case, we would be 2 standard deviation units below the mean. Again, within one standard deviation unit, we are considered a common score. 70% of the scores reside within one standard deviation unit above and below. So this puts us outside of that common region on the negative side. So in this case, we would not prefer to be part of that distribution. Let's compare it to the next distribution. So if we have a distribution that's flatter, has greater diversity, more variability, we still have the mean in the center of 78, but now with the standard deviation equal to 8 points, if we go out one standard deviation unit, that puts us at our score of 70. All right, so this is -1 standard deviation unit. Again, if we use our equation of z equals score, 70 minus 78, divide by a standard deviation of 8, z is equal to -1. Okay, so in this case, we would prefer to be part of this distribution with standard deviation equal to 8, because that puts us in the common region, not an extreme score on the negative sign. So we're still considered a part of that group that's defined as the norm, the most highly occurring scores, or scores with the highest frequency. B says, if your score is equal to 80, which standard deviation would give you a better grade? Standard deviation of 4 or standard deviation of 8? So let's see how this is similar or different from the previous example. So we have a distribution with the standard deviation equal to 4. I'm just going to make that a little more consistent looking. Okay, so we have a mean of 78. Our score is 80, but let's first consider what one standard deviation unit will take us to. So one standard deviation unit, when it's equal to 4, would put us at 82. And our score of 80 would be here in between those two scores. May not be as evident here until we do our calculations. So let's consider Z is equal to score 80 minus our mean 78 divide by 4. So we take 80, subtract 78, we get 2, divide by 4, and we get Z is equal to positive 0.5. Okay, now let's consider the next distribution that is more diverse, more spread out, and we have a mean of 78. One standard deviation unit above, right? If we go 8 points up, that takes us to a score of 86. And again, our score of 80 is in between those values. And to better assess which distribution places your score of 80 in a better position, we take Z is equal to 80 minus 78 divide by 8, and we get Z is equal to positive 0.25. So this score of 80, when the distribution is more diverse, places us at a quarter of a standard deviation unit above the mean, and in this case we were half a standard deviation unit above the mean. Both would place us in that common region. Nonetheless, the distribution where standard deviation is equal to 4 places us further from the mean, which is a better scenario. So we would prefer the more consistent distribution when we're on the positive side of the mean. Number 23, a distribution with a mean equal to 38 and a standard deviation equal to 5 is transformed into a standardized distribution with a mean equal to 50 and a standard deviation equal to 10. Find the new standardized score for each of the following values from the population. So essentially what we're doing is taking an original distribution with a mean of 38 and standard deviation equal to 5 and converting all of these original scores into z-scores to then help us produce a brand new distribution where we've identified the mean to be 50 and standard deviation equal to 10. So we're going to create new x values. So the first step is to convert our scores into z-scores. So I'm going to place my x values here and then show you step by step of how we would calculate our z-score. So we have a score of 39, 43, 35, and 28. Just going to clean this up here. And then we're going to convert those into z-scores. So z is equal to x minus the mu divided by standard deviation. So if we take 39, I'll take 39 minus the mean of 38 and divide that by our standard deviation of 5, we get a z-score equal to 0.20. We take 43 minus 38, divide by 5, and we get a z-score equal to 1. 35 minus 38, divide by 5, we get a z-score of negative 0.60. 28 minus 38, divide by 5, and we get negative 2.0. Okay, so those are our z-scores. Next, we're going to convert those z-scores into new x values that have a predetermined mean of 50 and predetermined standard deviation equal to 10. So again, we're creating new x values. So we had our original x values, these are our new x values. So x is equal to, and again, x is equal to the mean plus our standard deviation multiplied by, let me just backtrack here for a second, mu. Mu is equal to, x is equal to mu plus our standard deviation multiplied by our z-score. Okay, so x is equal to the mean, this new mean of 50 here in the problem, 50, right, plus the standard deviation, the new standard deviation is 10, multiplied by the z-score that we just calculated, that was 0.20. So we get a new x value equal to 52. Next one, x is equal to the new mean of 50 plus the standard deviation of 10 multiplied by a z-score of 1. And we get, let me just change that 1, to an x value of 60. Okay, so then we have x is equal to 50 plus our standard deviation of 10 multiplied by the z-score of negative 0.60, and we get an x value equal to 44. Finally, x is equal to 50 plus 10 multiplied by negative 2 gives us an x value of 30. And visually, this is what we've done. We've taken an original distribution. We had an original distribution. Let me just... and we had the original mean, which was equal to 38. And we had scores above the mean of 39 and 43, and scores below, which were 35 and 28. Those were the original x values. Then we converted them into z-scores. So we interpreted those into how many standard deviation units they were from the mean. So this was negative 2 standard deviation units below the mean. Score of 35 was negative 0.6 standard deviation units below the mean. The mean is 0 standard deviation units from the mean. Score of 39 was 0.2 above the mean, and the score of 43 was 1 standard deviation unit. And then what we finally ended with was our new x values, new. So given the location of these values, again, we're not changing the distance between the mean. So given that we know the distance of the original scores, now we can use that distance to calculate the new values. So 39, right, became a score. So the new mean, the predetermined mean, was 50. That was given. Using that, we were able to convert a score of 39 into a score of 52, and a score of 43 into a score of 60, and a score of 35 into a score of 44, and a score of 28 into a score of 30. So again, the original distribution converted to distance and standard deviation units, z-scores, and let me just clean this up over here. I should just have z-scores off to the left here, z. And then using that distance, we just created new labels for these scores given the new mean and the new standard deviation. So again, it's just a process of standardizing scores, taking original scores, converting them into their distance expressed as standard deviation units or z-scores, using that information with the predetermined mean and standard deviation to calculate new x values in a distribution. Number 25. This incorporates a lot of the skills that we've learned in the past since chapter 3. So calculating the mean, the standard deviation, z-scores, and then also converting a distribution into a standardized distribution. So let's begin by computing the mean and standard deviation of this population of scores. So we have scores of 0, 6, 4, 3, and 12. And we're asked to calculate the mean. The mean is sum of x over n. We know we have 5 scores. We need to figure out what the sum of x is equal to. So sum of x, if we sum this column of 0, 6, 4, 3, and 12, we should get 25. So 25 over 5 gives us a mean of 5. Next, we want to calculate the standard deviation. I'm going to use the computational formula beginning with SS. So SS is equal to the sum of x squared minus the sum of x squared over n. I'm going to replace the variables I already know. I know the sum of x because I just calculated the mean, which is this is 25. We're going to square that. I know what n is equal to is 5. So what's missing is this, the sum of all x values that have been squared. Again, this is the process of using the computational formula. I'm going to square all my values and then take the sum of all x values that have been squared. So if I add 0, 36, 16, 9, and 144, I should get 205. So replace that variable. So again, order of operations says I square 25, divide by 5, and subtract from 205. So SS is equal to 205 minus 125, and that gives me 80. Now that's the sum of squared deviations. I want the average of those squared deviations, which is my understanding of variance, which is SS over n. We have 80 over 5 gives us 16. That's the average of squared deviations. I want to bring it back into its original unit, so I'm going to take the square root of my variance. The square root of 16 is equal to 4. So what we've done here is we've calculated the mean of 5 and the standard deviation equal to 4. So I'm going to carry that to the other next page, and we'll see that given these original scores, we can now convert those into z-scores with these statistics or parameters of the population mean and population standard deviation. So now we're going to convert our scores into z-scores. So our scores again were 0, 6, 4, 3, and 12. We're going to convert those to z-scores. So z is equal to x minus mu divided by our standard deviation. So our first z-score is calculated by taking 0. So our score is 0 minus 5 divided by our standard deviation, which was equal to 4. And we get a z-score equal to negative 1.25. So again, we're taking our score of 0 minus the mean of 5, divided by standard deviation equal to 4 is negative 1.25. Next one, z is equal to 6 minus 5, divided by 4, and we get 0.25. 4 minus 5, divided by 4, we get negative 0.25. 3 minus 5 divided by 4, and we get negative 0.5. 12 minus 5 divided by 4 gives us 1.75. Okay, so now what we've done is taken our original scores, and now we've expressed them as standard deviation units, whether they're above or below the mean of the distribution. Alright, so we've taken care of A and B, and now C says let's transform the original distribution into a new population of 5 scores with a mean of 100 and standard deviation equal to 20. So again, this is the new distribution. Actually, I'm going to write it up here. The new mean is equal to 100, and the new standard deviation is equal to 20. And I want to create new x values. So x is equal to mu plus standard deviation multiplied by z-score. Okay, so this new distribution, taking into consideration where the original scores resided in relation to the mean. We know their distance, so x is equal to the new mean of 100 plus our standard deviation 20 multiplied by negative 1.25. That gives me a score of 75. X is equal to 100 plus 20 multiplied by 0.25, and that gives us a score of 95. X is equal to 100 plus 20 multiplied by negative 0.25, and that gives us a score of 90. X is equal to 100 plus 20 multiplied by negative 0.5, and that gives us a score, oops, I think I may have made a mistake here, 0.25, 1.25. I just caught my mistake. I wrote the numbers wrong. I should stop to check my math. So you are probably screaming at the screen right now. So I apologize for that. So let's go back here. This is where my mistake occurred. All right, sorry about that. Let's try this again. So x is equal to the mean of 100 plus 20 multiplied by 0.25. So in our calculators, if we multiply 0.25 times 20, that gives us 5 added to 100, and we get 105. So I had put the next value there. So that's 105. Next one, x is equal to 100 plus 20 multiplied by negative 0.25. Negative 0.25. And we get 95, which is where I had written what I had written before for the previous one. We get 95. Next one we have 100 plus 20 multiplied by negative 0.5, and we get a new score of 90. And then finally x is equal to 100 plus 20 multiplied by 1.75, so 1 3/4 of a standard deviation. And in our calculators, that gives us a score of 135. All right, again, all we've done is take an original distribution where the mean was equal to, our original mean that we calculated was equal to 5. And we had scores above the mean, which included a score of 6 and a score of 12. And below the mean, we had scores of 4, 3, and 0. 1, 2, 3, 4, 5 scores. Then we converted all of those scores into z-scores. So those were my x values. My z-scores then were 5 became 0, 6 became 0.25, 12 became 1.75, 4 became a z-score of negative 0.25, 3 became a score of negative 0.5, and 0 became a score of negative 1.25. And then, finally, what we did, this last step, was simply create a new distribution, so new x values. So the mean became a predetermined mean equal to 100, a A score of 6 became a score of 105. A score of 12 became a score of 135. A score of 4 became a score of 95. A score of 3 became a score of 90. And a score of 0 became a score of 75. So again, we have our original distribution here, right? Original distribution, and we calculated the mean and standard deviation for those distributions. Our z distribution, converted all the original scores into z-scores and expressed them as distance from the mean in standard deviation units. And then finally, our new distribution of scores. The location of the scores do not change. It's just the mean and the standard deviation have been changed, have been predetermined. So they would all be in the same location. We've just relabeled them by creating a new distribution of x values.